Okay, thank you all for your patience, living that double job life right now. Okay, today is officially our last content lecture, y'all. You've made it. You're still breathing. You've gotten to the end of this absolutely bananas school year, which follows the weirdest school years of all time. Like, it's happening. The summer is upon us. Final announcements. Okay, so P4 is due today, if you didn't know. FYI, our last day for office hours will be Friday, so we're not going to have office hours over the final exam week, but hopefully that's not too bad a thing because the TAs can't answer your questions about the final exam anyway. Just as an FYI, you don't get anything for leftover late days. The point of late days is to give you the flexibility to live life. So, if you have late days left over, you can use them on this assignment. You still are limited to a max of 3 late days. But usually I get a question around this time about that. Yes?
Well, max of 3 late days means the last day to submit is Saturday?
Yes, Saturday. Saturday would be our last day to submit. The final exam, one change, I know I said it was going to come out today. We've decided to push it to go out tomorrow evening instead, because this way you can go to section and you can ask the TAs whatever you want in section, and the TAs can answer it. But if the exam came out today, then they'd have to play this weird cagey game of not answering everything. So the final exam will go out tomorrow evening after all the sections are done. Go to section, ask your TAs anything you want to ask. I know the TAs have their own sort of review plans, but the point of section tomorrow is for review. The final exam is going to be group submissions. It is going to be open note, open online, whatever you want from that respect. It's just closed staff. So you can ask clarifying questions on the ed board, but we can't, answer questions for you. It will be due the Wednesday of finals week at 11:59 p.m. And then we are going to start grading this thing Thursday morning. So there are no late assignments, as always, with this, exams accepted. Does anyone have any questions about the final exam? Cool. Yeah.
So is it a time,
Nope, not timed. I will say it was authored to be roughly 2 hours of if you sat down and wrote it on paper, but you have the full time to do it.
So we can kind of say the trial residence return.
Yeah, you can start and stop and whatever you need to do. Okay. Yes, absolutely. Yeah. Mm-hmm. It's mostly design-based. It will have questions that look very familiar based on your midterm experiences and your exercises, things like that. Yeah.
With regards to working, collaborating with people,
Mm-hmm.
I recall you said we can work with 3 people, right?
Yes, these groups are up to 3. Please collaborate just within your group. Listen, y'all, I know. I've been a student. I know when I say open note, open book, open group, that there's probably, some group of you that meet somewhere and are going to talk through it together. I recognize that there's nothing I can do to stop that. And honestly, part of the reason the exam is designed is because even if you do chat, guess what you're learning? Okay, you think you might be circumnavigating the rules, but you're having some important design conversations that might actually help you be a better programmer. And I care way more about that than points or something. But please only submit a design that you and your group members worked on. Gradescope does have automatic sort of detection. So if you cut and paste a paragraph or your language or design looks too similar to another group's language or design, yes, that will be suspect. You are expected to submit group work for just the group members. The groups are optional up to 3 people. So you are okay. If you want to work alone, you can work alone. You can work with up to 3 people, just like your programming assignments. Nobody asked this question, but the topics for the exam are anything from last week to the beginning of the quarter. So technically this topic won't be on the exam, but everything through PNP could show up on the exam. Yes?
You know what regrade requests for the midterm will be processed?
Regrade requests, period, will probably be processed sometime in the next week and a half. It's just one of those things where we got a bunch of grading to do. We're going to get it done over the next week and a half or so. So when we get it done, we get it done, unfortunately. We'll try to get it back to you sometime during finals week so you can take a look at it. We'll see. Any other questions? Cool. Also, Friday's lecture, which we will have, we are actually going to spend it with the TAs. So the TAs have put together some great content for you. We've got a panel of TAs, all with very different experiences and directions in the tech industry. I know I've been talking a lot from like, I got an electrical engineering degree, then I became a software engineer, and now I'm like, you know, at Google, which is a very widely recognized pathway, but there's like a million different things you can do in tech, and you don't have to necessarily write code, and there's a lot of different ways to get to where you're going. So the TAs are going to come and talk a little bit more about their paths and the different ways that you can go. I also will be here, so we're just going to turn it into one big AMA. So anything you want to know about tech, career, classes, all that good stuff, that's what we're going to be spending our time on Friday doing. So come, hopefully it'll be a really great time, great conversation. Also, if you can't tell, I am quite an open book, and my TAs, bless them, have been forced to be such as well. So, you know, I believe in full honesty and transparency. That's how we get stronger as a community, y'all. So bring those questions. Would love to chat about it. It's a great opportunity for that. Any other administrivia questions between now and literally the end of the quarter? Yeah.
Submitting the final, so we can team up, but I guess I add my team member,
Yes.
just like any other project.
Yep. Add your team members on Gradescope just like your programming assignments. Yeah. Yeah. And that's why we made it 3, because I was like, how mean would it be if we made it out of 2 and you had a project group of 3? That'd be mean, right? So it'll function just like the projects. Yeah. Okay. Okay. Then let's talk about our last topic of the quarter. I'm biased. It's one of my favorite topics, and every other lecturer tries to cut this out of data structures and algorithms. And so I finally I was like, fine, we'll save it till the very end. This is the moment where theory officially stops mattering. This is all practicality, okay? Forget that frictionless surface that they make you think about in physics. Now you understand it. You've got your big O. Now we're talking about the reality of the speed of light is actually what we're talking about here. So you probably are aware that there is this magical thing called binary. And remember that what binary is just a base 2 numerical system, zeros or ones. And what that 0 and 1 means is like a light switch in your computer. If the switch is on, it's a 1, and that means electricity can move across the silicon of possibly your PNP transistor to get to the other side. And by combining literally thousands and millions of these switches back and forth, we've figured out a way to encode data and logic into the computer. But like I said, that actual switch, like the act of like click, switching your light on, inside the computer, that is the movement of an electron from one side of a semiconductor to the other side of a semiconductor. And that has physical limitations. It also, if that's just the transistor, we have to put these transistors in our computer in ways where this electricity has to move through this actual physical device. And some of these chips are further away than others. And also, electricity generates energy. Energy creates heat, right? So now we have to start to think in terms of when we're writing our code and we're asking our computer to do all these magical instructions, it's not just sending it off into the void and some beautiful, magical, instantaneous thing come back, but actually the energization of a bunch of electrons that have to physically transmit themselves through the hardboard in your computer. And that actually has a lot of impact on the runtime of your code. Let's talk about that impact. So here's a thought experiment. Here are two pieces of code. Sum 1 takes in an n and an m and a two-dimensional table. And it loops over n and then m. And then you can see the only difference between these two lines of code is this piece right here, where this piece is changing the rows on the outer loop, and this piece is changing the rows on the inner loop. So, what is the big theta of these items? We can see, well, they're in a nested loop. N and M seem meaningful, so they both have like a theta of N and M, right? Like the only difference between these two items is two characters that are swapped. They have the same asymptotic analysis, same code model even, right? Which do you think runs faster? Ooh, yeah, what do you think? The left one. What do you think?
I was going to say the left one as well.
The left one? I hear lefts. Does anybody want to give us an example as to, or a reason why? Yeah, what do you think?
It's something by the rows, and the rows are like memory slots in adjacency. So it just goes down a row, down a row, down a row. But the other one is something by column, so it's looking at the first one for each of those arrays.
Yes. It seems like it has something to do with the rate at which we're accessing this two-dimensional array. Remember a two-dimensional array? All a two-dimensional array is an array of arrays. So in the left-hand one, we're pulling out the first array, and then we're going from index 0 to end of the first array. And then we end the inner loop, and we go to the second one, we go 0 to the other one. Versus in sum 2, we're going to do all the index 0s of each array, and then we're going to do all the index 1s of each array, so on and so forth. Any other thoughts or guesses about this before I reveal the answer? Okay, here is a graph of my old Surface 5 running these pieces of code. The blue line that looks almost identical to the x-axis down here is sum 1. This red line with this concerning spike is sum 2. So this is a visualization of how, in this particular case, we can leverage spatial and temporal locality to cooperate with the caching systems of our computer to actually produce more efficient code. Now, the reason that this lecture always gets cut from this class is because, frankly, software people don't care about this. Software people are like, I don't know, it's theoretically the same. What does it matter? But then you, my wonderful non-CS majors, you show up and you're like, aha, I am a well-rounded engineer. I have context. Casey told me it matters. And you get to be the lone voice in the room that's like, but did you think about caching? And you shall win the day. And then you should like Facebook message me or something so that I get to live vicariously. Okay, how does this work? Yeah, question.
Why does it look like someone is not increasing exponentially in like the...
Because this number down here is 60,000, and that is still such a small number that this still looks almost constant instead of what this really is like, yeah, like depending on the size of n and m, right? This is almost an n squared situation. Yeah.
Do you know like the reason for like those jumps that we see?
Yes, I do know the reason for those jumps. What an amazing segue. So, okay. Incorrect assumption. Accessing memory is quick and a constant time operation in all situations. Lies. But was really convenient for code modeling, and also maybe do you appreciate now why Casey was like, wave away those constants. We don't care about those things. Okay, I'm sorry. Now we're going to start to care about the reality of things. Sometimes accessing memory is just cheaper and easier than at other times. And I'm going to talk to you about why. Sometimes accessing memory is incredibly slow. And in fact, those spikes that we saw in that graph are moments when accessing memory is especially slow. And I'm going to tell you why those moments happen. So, meet the RAM, the random access memory. This is like a stick, a RAM stick. This is the front and the back of it. And you can see these little clusters here. These little chips are just clusters of transistors that act as giant data storage. You can literally think of this as an array of arrays. Get it? It's a stick with all these little clusters in it, and the clusters are actually just addresses with a space to store something. That's all RAM is. It's an array of arrays. Everything's an array under the hood. RAM goes by a ton of different names: memory, main memory, et cetera, all the same thing. If you ever open up your process, okay, this looks a lot like Casey's processor from 2 years ago. You know, like when you see all these things, the RAM is the stuff that stores the things your computer is actively doing right now. In fact, for the RAM to be functional, it has to be powered on, meaning like when you turn your computer off, the RAM kind of just like, it forgets its stuff. It needs that constant flow of energy. This is a different type of memory than, say, like your hard disk. That's a long-term storage-y solution, so when you turn your computer off, you don't lose all your pictures and stuff. This is instead, it's usually smaller and faster and requires that memory, and it's what's managing the active programs that are happening on your computer at any given time. So, for example, when you run your program and then you get that Stack Overflow error, what that actually is Java and your operating system are smart enough to know that your program is sharing memory space with, I don't know, like PowerPoint and Chrome and Sublime and whatever the heck else I was doing in here. And if you let your program just consume infinite amounts of memory, it's going to crash the other programs that are running on your computer. So RAM puts these sort of boundaries around how much memory your individual program can take up, because otherwise it's just going to like literally like overwrite other spaces in memory because it's all the same memory under the hood. So it's a huge array. Look it, you can watch this delightful YouTube video. Yep, great. And so I know I sort of like talked about this at various times when we were like, but Casey, linked lists don't have that annoying resize situation. So why aren't we using linked lists at all times? Why are we so obsessed with arrays? That's the other thing we're going to answer today. So this top version, think of these like big arrays here. These are open available spaces in the RAM. It is your operating system's job to manage the RAM. I like to think of like the operating system and the RAM as like your dad packing the car for a big road trip. And by your dad, I mean me, because I'm packing the car for the road trip. And you all think you can just pack anything, but nobody is going to put stuff into the back of the car until I have personally like organized and tessellated it in there, because I know best what's going to fit in the back of the car, right? So it's your job to come over and put your bags by the back of the car and be like, hey, can you please find a place for this somewhere in there? And it's my job to pick it up and put it somewhere that fits. That's the operating system. Your program is my sister, who does not understand that you don't need that many shoes for a weekend away, right? So what has happened is my sister has shown up and she said, hey, Casey, can you pack me a new array of ints? I got 3 ints. And I'm like, oh, an array? Heck yes, I can. I'm going to go and find a contiguous block in memory. Whenever I am storing an array in RAM, I'm going to go find a series of spaces in memory that are all free and all right next to each other. Meaning these 3 pieces of data are always going to be stored as neighbors. That is very different than if instead you showed up with the same 3 numbers as linked list nodes. In that case, I know I can break those things up. I don't know, maybe I have like a corner available over here and a corner available over there and a corner available over here, and I'm going to put them wherever the heck I want to put them. They are not intrinsically linked in the eyes of the operating system as to where in the RAM they should be placed. And this is also part of why it actually just takes longer to loop over the numbers of a linked list than an array, because what would happen if I was looping over this array is the computer would come in and it'd be like, oh, here's the first item. Well, I know the second item's right next door. I know the next item's right next door. That's a lot of a faster operation than I maybe start here and then I got to look next door to find my like pointer, and then I got to jump to wherever the heck that pointer is, and then I find my item, and then I got to jump to that pointer. So right here is an example of why, even though asymptotically, even though theoretically linked lists may show up to be more efficient than arrays, the physicality of how things are stored in your RAM does impact this runtime, and in this case, an array would operate faster. Yeah.
Wait, so does this mean that for linked lists, they take up more space than arrays do because you have to store the pointer?
So per individual item, linked lists will always take up more space because they have to store the data and the pointer. Arrays only store that individual item. However, when you make an array, usually you have to make a bigger array and there's like unused space. And so the balance you're making is like, okay, a little bit of extra space per item or unused space per the group. So sometimes more, sometimes less, depending on that. Yeah. Do you have a question? Did that answer it?
Yeah, it was kind of like digging into that.
Yeah.
The pointers you have to consider, but it doesn't necessarily like, I'm assuming like the functionality of it. For example, like the .next functions are like stored somewhere else.
So when we call .next, if you remember, we call .next, there's no parentheses, right? It's a field, right? And so what that means is when I call .next, it means go to the location in memory that stores .next, and guess what's stored as a .next? It's a memory address. So these arrows that we draw, the thing that's actually physically stored in there is a number that is the index of that place in memory. So like right here, this little pointer that points all the way down here, this would actually be a hexadecimal number that would be the address of where this bucket is. Because that's what the operating system knows how to do. It knows how to take in memory addresses and then to find that location in the RAM.
So then, like, what about like the new node constructor? Because like arrays are kind of like inherent to the, the mechanical portions of a computer, while as like that's a class, right?
Yeah. So what's happening is new, that actually calls the constructor. The constructor, when compiled, will go in and partition space in memory based on the general space used of your object. And if your object constructor has two fields that are set, that means when you call new, it'll go in and partition two buckets for your two fields in that case, the data field and the next field. Yeah.
So why does Chrome take up so many of these memories?
Why does Chrome takes up so much memory, right? I don't know. Oh man, I'm just going to say something that's going to make me feel really old. So I remember when Chrome came out and everyone was like, why do we need another browser? Internet Explorer won the browser wars and they fight dirty. And frankly, the 90s was very about that. And then Chrome came out, which also, fun fact, was literally a Googler 20% project. And the reason that they invented Chrome is because they were like, wow, Internet Explorer has very firm boundaries on what it supports and how it interprets things. And we want Chrome to work really well on a lot of different things. So Chrome can process a lot more libraries, a lot more just sort of updates. It keeps web pages looking good, fewer things break. And so it's doing a ton of API calls and managing things. And also, it's doing a massive amount of data collection. That's real. Every time, and I will say this if I haven't said it, anything that's free in this world to you means that you are the product. So if you're like, wow, sweet, super cool software download, that's not the product. The software download isn't the product. You are the product. So you are Chrome's product. That is then use that data to collect and track your movements and factor it into our ad revenue, et cetera, et cetera, et cetera. But doesn't it work really good? Do we really care that much about privacy? You decide. But that is absolutely one of the reasons that Chrome has so much overhead. So how does the general memory of your computer work? So at the core, at the very center, we have this magical thing called the CPU, the Central Processing Unit. And that is the brains. And that thing has to be super fast. So it doesn't have a lot of storage around it, right? It only has enough storage to sort of have one or two things that it's operating on and then one thing on deck. And it needs that because it needs to be super, super fast, because the speed of your CPU is generally the speed of your computer. Remember that even though your computers seem to be doing a ton of things all at once, actually, your computers can only do a single calculation at any given time. It's doing those single calculations at the speed of freaking light, so it feels like it's doing a ton of things. But remember last week, and I was like, we're at the limitation of what computers can physically process when we get into the NP hard and NP complete categories. That's because computers can only do one thing at a time. If you're interested, quantum computing is the idea of letting your computers do multiple things at once, like a human brain. That doesn't technically exist yet. But UW is actually one of the foremost research institutions on that next development and a very interesting next frontier of computing. But right now, we live in this land. We live in a CPU land. We do one thing at a time. It typically can handle about 32 bytes of memory at once, and it is literally operating so quick that it is operating at the speed of light with essentially no distance to travel. So we think of the time that it takes for stuff to move through there as instantaneous being the speed of light. But we need ways to feed data efficiently into that CPU, right? I want to say at the very, very beginning of the quarter, I referenced oh my gosh, I just lost it again. Why does my brain do this to me? Because I want to say Spring Awakening, and that's a musical. It'll come to me. Anyway, God damn it. Wow, brains are a funny thing. I just lost the name of this movie. Okay, hang on. You guys know this. Miyazaki, Studio Ghibli, Afterworld, Bathhouse. Thank you, Spirited Away. Spring Awakening, not even close, brain. Brains are weird. See, I don't know why we trying to mimic brains, because they kind of crappy. Spirited Away, I think of Kumaji down in the boiler room. Like, he has not moved. He just has a million arms, and everyone has to bring him things. That's what the CPU is. He's making the whole bathhouse run, right? And it's everyone else's job to get the stuff there as efficiently as possible so that Kumaji has everything at hand's length. That's what the CPU is. So we talked about the RAM, but the RAM is huge, right? Like I showed you all those things that are running in the RAM. It's too big for the CPU to efficiently grab things from the RAM and feed them in with zero sort of downtime. So we have what we call caches, which are essentially staging areas for data of different size. So we usually have, it depends on your computer architecture a little bit, but pretty standard. We have an L1 cache that is a lot more memory than the CPU, but extra close to the CPU. And this is the stuff that's like on deck, coming up next. And so as the CPU finishes the thing it's working on, things just get automatically loaded in from the L1 cache. Then we have another layer slightly further out, which is even more memory, the L2 cache, but because it's bigger, it has to be physically further away. And now we're starting to incur the physical slowdown of the time it takes the electrons to move within the little silicon-like wires of your computer. Then, further out than that is the RAM, and that's way big. And also, we have to separate these things because of heat, too. Heat will corrupt the data because heat will excite the electrons and cause them to like jump in places they shouldn't be. And one extra transistor flipped in the way that we don't want it can change the hexadecimal number, which could change the entire memory address, right? So we cannot let heat corrupt things. So the actual design of your computer is very much about what produces heat and how far away do we have to keep things from one another, and also the like fan airflow and stuff like that. Further out from the RAM and orders of magnitude slower is what we would call the disk. And like I said, the big difference between the RAM and the disk is the RAM, it's really fast because it runs on electricity. As soon as you turn the computer on, it's got electricity running, it's humming, it's ready to go. But it loses all of its memory when you turn the computer off. We need something that can maintain your data when the computer's off, but in order to do that, that means that it has to be maintained with something that's not a transistor, right? So, once upon a time, we had these things. They were called tapes, and it was a magnetic piece of tape, and you actually magnetized this tape, and it changed the structure of the tape, and you would like put it into things like a VCR or like a tape deck. Or when you're a KC champion, you're an intern at NetApp, actually the vast majority of the government files are stored in contractors like NetApp or in massive warehouses still on tape, because we can temperature control tape and it doesn't degrade for about, I think it's like 100 years. Fun fact though, it was degrading while I was there, and a bunch of my intern friends' jobs were to take really old ass file tapes and digitize them. That was a real thing. Also, you can kind of think of disk like, you know how when a record plays, technically the sound that's coming out is the little record needle over little bumps on the record? When you have what we call a spinning disk, like if you can feel movement in your computer and there's like a corner that gets really angry and hot, a lot of you have what we call disk type memory in your computer, which is essentially a record, but it is now fancy. Instead of like, I don't know how they actually make records. I don't know what tool they use. I'm going to be real. But it's like, once upon a time, we had these things called CDs, and you would burn a CD in your CD drive. And what that was is an actual laser making laser little cuts on the CD. It's kind of like that. That's what's happening out in the disk drive. Because once you make cuts, I don't need electricity to remember that, right? But to interpret that data way the frick out in the disk and to find it on that spinning thing and to interpret the scratches, we are now working in orders of magnitude slower to get data from there all the way to your CPU. So you can see this crazy jump in the time it takes to get one piece of data from the disk all the way to the CPU. Yeah?
I'm assuming that the disk is, like, from the way you made it sound, it's sequential, right?
Sequential meaning?
Like random access memory is like you can store things
Ah.
jump to it, but like you have to unwind and rewind it.
Yes, exactly. Yes. Interesting point. Random access memory, the joy of it is I can jump into any spot because of the electrical like sort of setup of that. But the disk, like you just mentioned, is sequential. Like if I wanted to listen to a audio cassette tape, I would have to put it in and rewind it, which would mean move the tape to a different location to get to that access of the data. That's also what's happening in your computer. That's part of why it's spinning all the time, because it's trying to get you to the right spot on that physical thing to get the piece of information you're looking for. Yeah. So you can delete stuff from a disk by changing the way that it is sort of like inscribed. And so like there are like reburnable CDs, but after you do it a certain number of times, the data does degrade because you are making permanent changes to the CD. But they are so small and the computer's really smart about how to leverage them and change them a little bit that you can reuse them to a certain degree. But this is also the reason why, okay, just out of pure interest, have y'all used CDs? Okay, cool. Has anybody here used a cassette tape? Okay, some, okay. Okay, how many people here have used a floppy disk? Okay, all right. Okay, wait, when I say floppy disk, was your floppy disk actually floppy? Or was it like hard and stiff? Hard and stiff. How many people are here have used a floppy disk that you can wave around? Yeah? Okay. Congratulations. Me too. Let's do it. All of those things I just listed are tape. There's tape underneath the hood of all of those things. And the old floppy ones, you could see the tape and then they were like, ooh, that's bad. People get their like gross fingers on it, and that's why they made the hard versions. And also, if you've used CDs, if you ever dropped a CD perhaps on the floor of your 97 Jetta and then your friend Jamie stepped on it while you were at McDonald's, now you can't listen to Avril Lavigne anymore because the CD got scratched, right? All part of the physical changes of the CD. Yeah, question. Oh, how do SSDs factor into this? So solid state drives are a type of disk, but a type of disk that doesn't require the spinning rotation. And because it doesn't require the spinning rotation, you get a lot more optimal heat usage, but they can be a lot more expensive. And I will fully admit, I don't know as much about them as far as how they actually mark the data. But the reason they're called solid state is because they don't have that like whipping action of the disk usually. Yeah.
So on like a desktop computer, is the L1 and L2 cache built into the CPU chip?
So these are all things that would be built on somewhere on those like green boards. You will probably find the motherboard of your desktop computer includes a CPU and one of the caches, but then the other caches and the RAM would be on separate places usually. mostly for or for heat management. Yeah.
What's the limitations of just like other than heat putting just a bunch of cores onto like one CPU, like just putting all the caches on one chip?
So okay, so there's two questions in there. Cache is different from cores. Cores are brains, right? Yeah. So you can have something called a dual core machine, but think about how complicated it would be if like there were two kings, right? Like they got to figure out who goes what. Imagine how much more complicated 3 kings or 3 presidents would be. That's why you don't really see like triple core or quad core, too much beyond that, because the way that you interweave the instructions with the actual brain of the computer gets really complicated, and we just don't have computers that are ready for that. Quantum computing. Caches, yeah. If you are a fiscally reminded individual who is able to open up your computer and change these cards out, probably the first thing you're going to do is go buy a bunch of way better memory cards and like load up your computer. And is usually one of the things that like they do as a main spec of your computer when you're purchasing it, right? Like we look at the disk size, we look at the RAM size, but you can add in as much memory as you want usually, but you are physically limited to the size of your board. And usually you're competing for space with like your graphics card and all that stuff too. So, yeah.
What does clear your cache actually do then?
So when we say clear your cache, what we mean is these 2 items here to remove all of that stuff from there, which is the stuff that's sort of like next in line for the CPU register. Now, in terms of browser stuff, it can be stuff that's actively stored in these caches. It sometimes can be stuff that's also kind of secretly stored in the RAM because it depends on how much we're getting there. And if you're like storing all of your browser history for an elongated like internet session, it probably is going to be larger than the cache. But usually what it means is just clearing out these things here, which a lot of times can like improve the runtime if you're trying to transition to a new program or something, because it's like trying to say like, hey, I don't care about, that old program that was running in the background, clear that out. So now that we know this about memory, how can we use this to write more efficient code? So I think we talked about this. The general takeaways is the more memory a layer can store, the slower it is. And accessing the disk, super slow. You got to go out and get like documents or music or video files, which are never going to be small enough to store in your RAM. That's going to take a long time. And you're limited by speed of light, physical closeness to the CPU, and also memory tends to get very expensive, and you have to balance how much memory with how fast it is. So when you're purchasing your own memory sticks, you can probably get a lot of memory pretty cheap if you're down with it being kind of slow. Yeah.
Can you go back to the previous slide real quick?
Yeah.
What's the reason again that the larger the size of the memory is, the farther it needs to be away from the CPU?
It's not necessarily that it needs to be, but it's just like when we think about design principles, we want to like sort of like build this sort of like waterfall set of layers. And the reason that sometimes we make those things that are further out larger is because operating systems have 2 different ways of thinking about groups of data within a piece of memory that's storing it. So the 2 things that we think about are spatial locality and temporal locality. Spatial locality, kind of to your question, is the idea that if I've used a piece of data, chances are I'm going to use the neighbors immediately around that data sometime soon. This comes from the idea of arrays, or like our nodes, those fields. If I access the data field of a node, chances are I'm going to access the next field of that node. If I accessed index 0 of an array, chances are I'm going to access index 100 of that array. Those things are typically physically stored as neighbors. If I use one, chances are I'm going to use another. Then there's temporal locality. Temporal locality is the idea that if I have just used a piece of memory, chances are I'm going to access it again in the future. I think a temporal locality is that like pile of clothes on your office chair that it's like, I just wore it once and like it's not ready to go in the laundry. So I'm just kind of like live off the top layer of those clothes, And then like if I have to go get like my, winter coat, it's like way deep in the back of my closet because I don't need it as much. But like Casey's comfy stretchy pants are like always ready at hand because I use them most recently. Temporal locality, if you most recently used it, chances are you're going to use it again. Spatial locality, if you used one neighbor, you're probably going to use them all. So, leveraging spatial locality. When we are asking for information from anything, especially if we're going to a slow layer like the disk, I'm going to try to bring back with me as many things as can fit in the car. If I'm going to go all the way out to disk and get a piece of information, I'm going to grab more than that immediate piece of information that was asked because I'm going to try and optimize the time it took me to go out and back. And I'm going to grab all of the neighbors of that piece of data, hoping that the stuff you're going to ask for next is like co-located with that stuff. We think of this as the data carpool, and that's because these ways to go out to the disk and back come in these set sizes. And so your car is going to take the same amount of time to drive to the store if you pick up one can of soda or if you pick up flats of soda, right? So spatial locality is the idea that it's like if you're going to drive all the way out to the disk, you better fill up the trunk because we don't want to make that trip more times than we need to. And if we're going to make a guess, chances are if you grabbed one neighbor, we're going to grab them all. I did not make these slides. But shout out to Zach, my head TA, who did make these slides. Also, we're not remote this quarter, so I don't think y'all have met Mercy, but this is my cat, Iron Fist No Mercy. And I used to live across from the Sketchway. Yeah, I know. You could see me from my window. It was really awkward for y'all, but I had a good time. I don't live there anymore, unfortunately. So let's say we are at home in Casey's apartment and Mercy is hungry, because she always is, and she wants to get some fish. So Casey can walk across the street and get a fish, and we can bring back a single fish, and then she eats it, and now she's hungry again. So we gotta go and get another fish and then eat it again. And then we gotta go and get another fish and eat it again. Wouldn't it be convenient if we had a way to grab more fish than Mercy can eat, but have a way to store it so it doesn't spoil in the time that she gets to it, so I don't have to make quite as many trips? A refrigerator. A refrigerator is like a temporary storage between the store and your mouth that keeps your data ready for you to use, but lets you go to the store and like fill up the trunk so you don't have to go back out to the store every time Mercy's hungry. The refrigerator then can store all your fish. Mercy's happy. We take fewer trips to the store. In this analogy, the CPU, I guess, is Mercy, which makes sense. And the RAM is Safeway, and the refrigerator is the cache. That lets us go out to slow layers, and the RAM is considered a slow layer, and get that stuff. Here's a bunch of stuff you can read about caches. I'll let you read it. This is a big idea. This is about how much memory you grab from the cache, et cetera, et cetera. Same thing with the slow layer. So the refrigerator is that idea of spatial locality. I go out, I grab as much as I can, I keep it in the cache as close as possible. Temporal locality is about how you jettison things from the cache. You essentially keep the cache full at all times. And you kind of rotate things in and out. And so when you're deciding what to rotate out from the cache, you always rotate out the stuff that was touched the longest ago. So by leveraging the temporal locality and the spatial locality, spatial, we go grab as much as we need, we fill up the cache. When we're trying to decide who stays and who gets jettisoned from the cache, we keep the stuff we most recently used. That is generally going to keep, yeah, okay, fine. Here we go. That is going to help us with this particular sum situation where, again, think of it as an array of arrays. This left side sum, when I went out to the RAM, it would have grabbed this entire array. And then I would have looped over A, B, C. This version would have gone, it would have grabbed this array, and then it would have grabbed this array, and then it would have grabbed this array, and then it would have grabbed this array, and it would have grabbed this array. And by the time it got to this freaking array, it would have already jettisoned